All right, so video number 2, we're going to move on to our alkyl chlorides. So we talked through the idea that if we're doing heterolytic cleavage back in video 1 with bromine, our heterolytic cleavage is going to be where we're pushing both of those electrons. So chlorine is going to also have heterolytic cleavage where we do that exact same process of breaking the carbon-chlorine bond and giving those electrons to chlorine. So our first fragment that we will have is going to be that carbocation. I skipped something. I went ahead and drew the molecular ion for this structure. So the same process as bromine, we are going to lose, one electron from one of the chlorine lone pairs. So I would see this in my mass spec with a mass to charge ratio. Now, we do not need to forget about the isotopes of chlorine. There is a difference in abundancy, and that chlorine is going to be a 1:3 ratio, where we would see 1 peak a third in height for fragments that contain chlorine, such as our molecular ion peak. But our first fragment here, once we do the heterolytic cleavage, is going to lose the chlorine, so I don't have to worry about the isotope. This is just going to be my propyl peak, which we saw from bromine is going to be a mass to charge ratio of 43. All right, so that's pretty straightforward. That's the same thing what we just saw. Now, additionally with our chlorines is we can do our homolytic cleavage. So our homolytic cleavage is going to be using our fishhook arrows, where we're only moving, I don't even know what arrow that was. I literally drew a fishhook, I think, where we're moving just 1 electron at a time. And another term that we use for homolytic cleavage is alpha cleavage. And my reasoning with that is because you're using the alpha carbon. All right, or we're talking about the alpha position. So let's look at this. Usually students ask me, where do you even begin? I don't even know where to start. Well, my starting spot is usually the radical, just because it's the one thing that is most unusual about the structure. So it's a good starting point, a good focal point for me. And whenever we're doing alpha cleavages, we're usually forming pi bonds. So what we're going to do is we're going to take this radical electron and we're going to begin the process of forming a pi bond with chlorine and carbon. So we're going to use that electron to begin our double bond. Now, a bond is made up of 2 electrons, so I need to take an electron from somewhere else. Well, I could take it from either this sigma bond or this sigma bond. In this case, it truly doesn't matter because they're both methyl groups. So I'm going to get the same fragment. Now, if they were not the same, let's say we had an ethyl group here, I would get a different fragment depending on which way I cleave this. All right, if you guys keep watching the videos, I will show you that with the ether, which is not symmetric, whereas this guy is symmetric. All right, so for now, we're just going to focus on the alpha cleavage. So I'm beginning that double bond by taking the radical electron and starting the process of the pi bond. I need to finish it. Now, again, it doesn't matter which sigma bond I use, but let's just use this guy. I've now finished that pi bond because I have used 2 electrons to form the double bond, but there were 2 electrons in this sigma bond. So the other electron needs to go somewhere. Well, I'm just going to put it on the carbon that did not form the double bond, and that should be it. So now, this carbon is no longer bonded to the rest of the structure. It is now free floating as a radical because that's where I stuck that extra electron. And then I now have a double bond between my alpha carbon and my chlorine, and chlorine is still going to have a positive charge here. And then I still have this other methyl group bonded to that alpha carbon here. So if I'm interested in mass spec, I know it will see the charged species, the chlorine. So I'd want to know the mass to charge ratio for this structure, in addition to the mass to charge ratio of my molecular ion. All right, more math, yay. So 12 times 2 is 24. Chlorine has a mass of around 35. And then I should have 1 hydrogen here and then 3 hydrogens here. So I believe that just puts me at 4. 3, 4. Yeah, that looks good. Okay, now I'm going to do the calculator because I have learned my lesson from video 1. So 24 plus 35 plus 4. Okay, I'm getting 63. Now, this has chlorine, so I need to be worried about the other isotope. So this one specifically looked at the isotope 35, but chlorine also has an isotope at 37, so that's just going to add 2, so I should also see 65. All right, so those are going to be my peaks for my alpha cleavage. Let's look at our molecular ion peak. So here I have 3 carbons, that would be 36. I have chlorine on here, and then I have 3, 6, 7 hydrogens. Just gonna erase that. So plus my 7. Yes, because, okay, I was about to say, why was there not 7 here? Well, that's because I lost the methyl group, that's why. Okay, so here I'm getting a mass to charge ratio of 36 plus 35 plus 7. I'm getting 78. Again, this only accounts for one isotope, so I need to account for that other isotope at 37, and that's going to get me to 80. So if I was looking at the mass spec for the structure, I would look for my molecular ion peak, where I should see 2 peaks. These should be at a 1:3 ratio. I would have my heterolytic cleavage. Now again, because this does not have chlorine anywhere on it, I don't have to worry about isotopes or anything like that. And then my alpha cleavage here, I would look for 63 and 65. Because it does have chlorine, I need to worry about those isotopes. So let's look at the spectrum. Well, I have my, let's see, get darker color. All right, I have my 80 and 78, and I do see that this is a 3:1 ratio. That signifies that chlorine is present. I also have that 65, 63 also at a 3:1 ratio. And then notice I have my 43 that does not have the 1:3 ratio, which I did not expect it to, because this was due to the heterolytic cleavage. So I'm pretty sure I spelled that wrong. All right, heterolytic cleavage, whereas these, whereas only these 2 peaks were my alpha cleavage, and then this is just my molecular ion peak, right? All right, so hopefully that clarifies some aspects to our alkyl chlorides.